In the previous two lectures, we discussed single charge sensing in quantum dots using two kinds of charge detectors or charge amplifiers. One is the single electron transistor and the other one using quantum point contacts. So in this lecture, we will discuss single short charge sensing. What that means is you are sensing the electron in real time, and we will discuss the bandwidth issues and the impedance matching problem that has been faced by the conventional time average charge sensors. Those are the ones we discussed in the previous two lectures. And we also will discuss the basic technology of radio frequency single electron transistors and radio frequency quantum point contacts. Now, let us briefly look at the need of a charge measurement or charge sensing by comparing a current measurement versus charge measurement technologies. Okay. So what I have here is a simple technique which all of us have done at some point of time, is checking the resistance of a resistor using a multimeter. This is a representation of you are calculating the resistance by running some current through it and measuring the voltage across, or measuring a voltage or applying a voltage and measuring current through it. In any case, what you are doing is some kind of current versus voltage measurement. There is some amplifier inside this unit, and you will get an output which will be amplified by certain factor. What are the gain of the amplifier? Those are the details which are not really relevant for this discussion. Now, the current through the circuit basically consists of charges shuttling through the circuit in a discrete manner. Okay. And the finest unit of the charge is the electronic charge. So the current is given by the average number of charge shuttling or traversing per unit time. The motion of the charge through the circuit has a statistics built into it. What I'm trying to say here is at some point of time that would be n electron, maybe the next moment could be n plus 1, or another moment could be n plus 2, and there is a statistics or a fluctuation built into it. If any time into delta t, the most probable number that would be going through is this average number n. Okay, but there is a fluctuation into that. It could be like n minus some number, n plus some number. But on an average, there is a distribution that is given by something like this. There's some kind of a distribution built into it. Okay. And for perfectly classical systems, which doesn't have any correlation between the electrons, similar to people walking through a pedestrian crossing. Okay. then this distribution will be more or less symmetric. And the peak will be at this value n. But when you measure the current, what you are actually measuring is this average number. But since there is a distribution built into it, there are other relevant parameters such as the higher moments of this distribution, such as the variance, which is the width of the distribution, skewness, how symmetric the distribution is around the average number n, or kurtosis, how sharp this distribution is. All these are very, very relevant parameter whenever you have correlated transport of electrons. You can have interesting phenomena such as short noise suppression, bunching and anti-bunching effects. All these things are there whenever there is a correlation built into it. And there will be noise suppression, which you cannot measure if you simply measure the average number, because you need information of the other higher moments of the distribution, which all these quantities are generally swept under the rug when you measure, when you do a simple current measurement. For example, a simple uncorrelated transport is similar to people moving on a street. There's nothing interesting. But a completely correlated transport, where it is similar to the march of army men, which they are all in sync and in rhythm, which has a far less noise. And this kind of transport will have a lot of interest, especially systems where you have electron-electron correlation, which are driven by various quantum mechanical interactions. All these effects you cannot detect or sense if you simply measure the average number, where you need the statistics or the moment of individual electrons. Okay, you need information on higher moments of statistics, which requires the moment of electrons, individual electrons, which you cannot get if you do a simple current measurement. Whereas for those studies, to get information on those properties, you need to measure the charge, not the current. And that also you need to measure in time scales where you can detect most of this motion, which forms the main topic of our discussion during this lecture. Now, let us look at the time scales of some of the electronic events that are interesting to us. Here are a couple of tables here taken from these references, and you can see that these lifetimes T1 and T2, one is the longitudinal lifetime, one is transverse lifetime or coherence time. T2 is the coherence time. Okay, these are all in microseconds to milliseconds, in that range. Whereas the scattering times in these solids such as gallium arsenide or silicon, these are the two main platform where one would like to realize advanced quantum mechanical devices. The scattering times are in picosecond range. And the orbital relaxation and all those other charge relaxation and all those things are really, really fast. Okay. What is shown here is these lifetimes or various time scale associated with spin states, which are the backbone of spin-based quantum computation scheme. Here is another table which consists of these times for silicon-based devices. And here also you can see the fastest one is your T2. That's again like half a second. You can see it has gone up to half a second. But mostly these are all again in a millisecond or a microsecond in that time scale. Now, the coherence time is in millisecond or certain time scale. What that tells you is you need to finish almost all the operations within that time scale. Those operations also involve various error correction routines, which involves detection of the spin state or charge state of the system by repetitive quantum non-demolition measurement. And those measurements need to be carried out at a time scale many orders faster than the coherence times. And these are generally done by some protocol called ancilla-based non-demolition measurements. Okay, and these mechanisms also need to go in parallel with the computation scheme as computation progress. And these readout times should be much faster than the coherence times, at least a couple of orders faster than the coherence times. So to realize this, what you need is a really fast charge sensing mechanism, which is relatively less invasive. Now, another demand for fast charge sensing comes from the charge counting singular circuits, which consist of single electron pumps, where your aim is to realize a quantum current standard by counting the number of electrons going through certain single electron pumping device, where you can pump electron by electron and you can standardize the current without any error, with far less error. And the latest development in this field is people have started now realizing gated quantum dot devices which actually can pump electrons in gigahertz rate, which actually nanosecond or faster time scale. So, but you also need, like many of the single electron detectors, placed in the same circuit where you are going to pump it, but at the same time you also need to detect the motion of these electrons through the circuit at the same rate. So this also points to demand of ultra-fast charge sensors for charge reading out circuit, which works in this rate or in the time scale, which is nanosecond or faster. So in all these instances, what we are seeing is there is a huge demand for charge amplifier, which works in real time, or you can detect the charge in one shot. Those are called single shot measurements, where you can detect the presence or absence of a charge and its dynamics too. Okay, and all this would be possible only if we have a detector which is really fast. And all the charge sensors that we have discussed so far in the last two classes are ultra sensitive, but they are very slow. And that is what the main bottleneck is. And in this lecture, we will take a quick look at all those charge sensors and also discuss some new technologies in this field where you can detect this charge motion in much faster time scale. Okay. Now here, in this case, this we have already discussed. What you have is you have a quantum point contact charge detector, and there is a gated quantum dot here, where you have a quantum dot here, and you have a quantum point contact that will exhibit a step-like feature whenever there is a charge motion, or charging or discharging even happens in the nearby quantum dot. And what we discussed is, in this side, when Vm is less negative, the level is inside the dot and the charge is inside dot, and here you are going in the negative direction where this gate Vm, this gate here is more negative, and this will push the level outside the Fermi level, and this electron will jump out. So what you have is, you're in this region you have the electron inside, here there is an electron outside. Now if you write it here at the middle of this event, then that corresponds to a situation where the level is in resonance with the Fermi level here. So you can have the electron jumping in and out because these two levels are resonant, and the sweep from this place to this place takes some time. So as it passes through the Fermi level, you can have the electron jumping back and forth, activated by the thermal energy of the system available in the system. And if you simply measure this, you will lose all those information about the temporal scales, how fast this electron is jumping out, how long the electron has stayed inside, or how long electron dot was empty, and all this all this information is lost, or it's not accessible to you if you simply measure the average current through the quantum point contact. That's what you're doing here. You're actually measuring the average current through quantum point contact using some kind of amplifier, and you're plotting that. But if you try to observe what happens at this point as a function of time using an oscilloscope, what you would see is, you will see that the current through the quantum point contact, IQPC, exhibit a two-stage behavior where the low current state happens when the electron is inside, and the high current state happens when the electron is outside. And this duration of the low current or high current state is telling you the occupation probability of the dot, and how fast, how long the electron stayed outside, and what is the tunnel rate, how many tunneling events are happening per second or per unit time. So in this specific case, what we are seeing is, you can see that the electron has stayed this duration outside, then it came and stayed this long inside, then again jumped outside, inside, and so on. So what you're seeing is, there are random tunneling events. That is what you would see when you have thermally activated tunneling. There are random tunneling events, and these time scales are random. It's a random telegraphic signal. But you can actually directly see where the electron is at a given instance. And this provides a lot of information about the state of the dot in real time. But now when we talk about real time, what is the time scale we talk about? The time scale in this case is dictated by, one, the bandwidth of the circuit here, and second, the bandwidth of the amplifier. When I say amplifier, that there are two amplifiers here. Okay, the quantum point contact themselves is an amplifier because it amplifies a simple tunneling event, a very minute tunneling event, into a large difference in the conductance or current. That's an amplification, but that's not the amplification I'm talking about, because it's quantum point contact, high mobility devices, they can operate a much, much faster time scale in tens of gigahertz to terahertz range. But what I'm talking here is the bandwidth of the measurement circuit and bandwidth of the secondary amplifier, which is connected at the end of the circuit. And as you can see, for these experiments, these bandwidths are in basically like a kilohertz, and this will be like tens of kilohertz. And how would you get this number? That we will discuss in a minute. This is another instance where one has used a quantum dot system, where you have two quantum dots here. Okay, and one of the quantum dot is a single electron transistor, and other quantum dot is the device that you are trying to probe. And as we know, when you bias the quantum dot, sensor quantum dot in one of the Coulomb block at oscillation, somewhere here or somewhere here, the current at this point is a strong function of the variation of the electric field. In this case, the current is going to fluctuate very sharply as this nearby quantum dot gets charged or discharged. And that is what is being captured here as the telegraphic signal. But again, you can see that the time scales that are in seconds here, the time scales here are also in seconds. So these events are like a millisecond or so in duration. That's the fastest that you can capture, and that is decided by the bandwidth of this amplifier. And that is the limitation now. We can detect only, by this method, we can detect only signals down to like a few milliseconds. But as we discussed, the demand is for amplifier which actually can detect in microseconds to nanosecond time scales, and the events are also in that time scale. Events that we are interested, the fragile quantum phenomena, and all those time scales of those phenomena, many of those phenomena are in microseconds to nanosecond time scale. And with this setup, one cannot detect those events. And that is what we want to look at. How can we detect, and what is the issue here, and how can we detect these events in much faster time scale. One of the first attempts to detect the real-time dynamics of electrons in confined systems such as quantum dots happened in early 2000s, where you have a quantum point contact and there is a quantum dot here, and this quantum dot can get charged or discharged, or the electron can tunnel in or out into the reservoir here from the quantum dot, and you have a nearby quantum point contact channel, and the current can actually show random telegraphic signal. But now the time scales are, in this case, are much faster than the ones we discussed in the previous slide. The reason here is there is an IV converter, which is a room temperature IV converter, which is actually a highly sensitive fast current preamplifier. But since you are still operating at room temperature and it is far from the device, but this device is at the coldest region of the measurement system. It's probably in the few millikelvin range, whereas this is at room temperature. And eventually, the detection bandwidth is limited by the noise of the IV converter, and that in this case, specific case, is limited to like 100 kilohertz, which correspond to like 10 microseconds in detection time. Okay, and this is one of the first attempts. And in another instance, you can have detection times again in similar, like few milliseconds. This is a 50 millisecond here, this is a 100 millisecond time scale. and again like few milliseconds. That is what these people have gotten for detection time, where they have a quantum dot here, electron can tunnel in or out, and they have two detection channels, two quantum point contact channels, and they have plotted the response of both channels, simultaneous response of both channels here, and both channels are registering same events, okay, and the same tunneling event of electrons observing, they are observing simultaneously. But again, the time scale is really slow. The fastest you can get, or fastest reported, just by using a conventional quantum point contact channel, is something like 10 microsecond in detection time. That's what we have. Okay. Now, the question is, what is limiting the operation? That is the main question. So let us look at a typical measurement setup. You have the device under test somewhere here, device under test somewhere here, okay, which is connected to the room temperature electronics through thin, long wires with a lot of filterings, because you need a lot of filtering arrangements to reduce the noise which is propagating from the room temperature into the device. So you have many meters of wires connected to the both source and drain side, and then you have certain amplifier which is connected to the device, okay. And remember, whether it is a QPC or a single electron transistor, these are high impedance devices. So what I'm trying to say is, both QPC and SET are high impedance devices. What that means is, this high impedance plus the capacitance of the long wire, okay, that is going to set up an RC time constant which is in the millisecond range. So this impedance of this QPC is hundreds of kilo ohm, when it's going to, in the sensitivity region is 50 kilo ohm to 100 kilo, in that range. And SET, again, that depends upon whether it is normal metal SET, then the minimum requirement is 50 kilo ohm, because you need 25 kilo ohm for both junctions, okay. That will be 50 kilo ohm. So again, what you're talking about resistance in terms of in the ballpark, in the range of 100 kilo ohm, plus you have many nanofarads of capacitance in the associated wiring. So all those is going to put the RC time constant to something like a millisecond range. Then another way to look at that is, you have a high impedance device sitting somewhere on the bottom. Here, what you're seeing here is a typical fridge setup, where we have fridges. What is used, fridge means it's a dilution fridge, which is used for this measurement, which has many meters of wires as I described inside, starting from room temperature down to the coldest region. And the device high in impedance, and these wires are low in impedance. So whenever you try to detect any dynamics at a faster time scale, you want to detect in gigahertz range or megahertz range. What happens is, whatever signal that you sent or try to detect in that time scale is going to suffer a huge impedance mismatch, because you have low impedance measurement wire and high impedance device. So the signal that is being reflected at the interface is huge. So almost all the signal is reflected, because the reflected signal gamma is basically Z minus Z0 divided Z plus Z0, where this is the impedance of the device and this is the impedance of the measurement circuit. So this is close to 1 almost all the time. Okay. So now what you are suffering here is two things. Number one, there is an low RC time constant. There is a RC time constant which is of the order of millisecond. And they have huge impedance mismatch. They're actually one and the same thing if you look around, if you look up. Okay. And finally, you also have this 1 by f noise because you are limited to low frequency range, where the 1 by f noise is also dominant. Then that is also going to contribute low signal noise ratio, which is going to affect your detection, signal detection speed and sensitivity. These are basically an issue, but if you look carefully, the intrinsic bandwidth of the device is really fast. The QPC has a really high intrinsic bandwidth. It can actually respond up to the terahertz range. So mostly you are now limited by your measurement circuitry, not by the device bandwidth. So intrinsic bandwidth of the fundamental amplifier we are discussing, that is the QPC, that is same for the similar single electron transistor, the SET also. The bandwidth of those are much faster. SET you can still control. You can still argue that it's decided by the tunnel rates, but that is also something which you can control. Okay. So in this case, we are mainly restricted or limited by the bandwidth of the measurement circuitry and impedance mismatch to achieve faster detection or faster amplification. And that is what we are trying to solve using a method called radio frequency reflectometry, technical radio frequency, impedance matching circuits. Okay, and that is what we are going to discuss for the rest of this lecture. So the idea here is very simple and straightforward. Remember, what we discussed is we have a high impedance device and a low impedance measurement circuitry. Measurement circuitry consists of conducting wires which are like a few ohms, and the device that the amplifier that you have is a quantum point contact or a single electron transistor. Those are hundreds of kilo ohms. Say 100 kilo ohm. Now, if you try to send a signal to the wire and get information back, in normal way, almost everything will be reflected because this impedance mismatch is almost like giving you a reflectivity of unity 1. Now, the idea here is you make some kind of an impedance transformer, okay, which is here, which consists of an LC circuit, and together with the R of the device, it becomes an LCR circuit. Okay, and the impedance of the circuit, when you look from the input side, that is somewhere here, this is the input side, is given by I omega L, that is impedance of this, plus parallel of RD and C, and that is this term. And this circuit will have a resonance, and omega 0 is 1 by square root of LC. And at resonance, the impedance of the device is simply given by L by C RD, that you can work out. At resonance, the imaginary part of this Z will go to 0. Then from that, assuming that you can get the impedance of the circuit at resonance, when you look from these points, okay, is L by CRT. Now you can come back here and you can make this Z 50 ohm by choosing L and C appropriately. So you can choose L and C to have Z equal to 50 ohm. That's the point. So if you choose appropriately L and C, and you can have this resonance at high frequency so that you are away from the 1 by f noise regime. So you can put this resonance at hundreds of megahertz to gigahertz scale by choosing L and C appropriately. So you can actually engineer the resonance frequency omega 0, and you can also engineer the impedance Z so that you don't get much reflection. Then what you're seeing here is the Z, the impedance is a function of the reverse resistance RD. So any change in RD is going to change Z, the impedance of the whole tank circuit here, and the reflected power also will change accordingly, because reflected power will be 0 when Z is Z0, but any small variation in reflected power driven by variation in the RD will be reflected, will be in the gamma measurement or in the reflected power measurement. For example, if your RD is fluctuating this way, then the reflected power at omega 0, all this discussion happens at the resonance, okay? Our point of interest is omega 0. At omega 0, this reflection is going to get amplitude modulated, okay, by the QPC impedance change or the QPC resistance change. This could be QPC or this could be a CT. In this instance, I have assumed it's QPC, but you can have a CT also. That is the idea here. Okay. So the point here is you are not measuring the current through the measurements through detector, whether it is a QPC or a CT, as in the previous case. In the previous case, what you are doing is you are measuring the current directly through this device, or current directly through this device. But that's not what you're doing now. What you're doing here is you are just measuring the reflected power from the tank circuit from this end. You send some signal and something will be reflected back, VR, and you are going to sense that. That will have information on the RD change, because you are interested only in change in RD. That's what you are doing here also. All you are doing is you are checking the impedance change, not the impedance, but in the change in RD and the time scale. But here it is limited to a few milliseconds. In this case, you are not limited to millisecond because you are detecting at a frequency prescribed by the resonance characteristics of this tank circuit with certain bandwidth, which are much larger compared to the your conventional measurement technique, conventional measurement regime. So the RD will change Z, that will change the reflected signal, that will amplitude modulate. So you are going to detect the change in the device impedance, the change in the QPC or the SCT impedance, just by looking at the reflected power of the tank circuit. That's what that's what the exercise you are going to do. Okay. And this is a landmark paper, and this is the first paper where the concept of radio frequency tank circuit or impedance transformer was applied to a single electron transistor. So what we have here is you have a single electron transistor, which is shown here. This is a small island formed by shadow evaporation technique, and this is a source electrode, and you have a drain electrode, and there's a gate also. And there are some other circuitry here which we are not going to discuss. And as we just discussed, this single electron transistor, which is represented by the double junction system, is connected to the external circuitry through an L and C. There is an L here, there is a C here. This is similar to what we have here. There is a L here, there is a C here. Very similar to this. And you are sending a signal, and there is a directional coupler which will take the signal down to a sample, and whatever is reflected from this end will be split from the input signal by the directional coupler and coupled to some external, some cryogenic amplifier and some room temperature amplifier lines, and eventually you will analyze the signal in the time domain or the frequency domain. Of course, the reflected signal will be amplitude modulated by the change of this impedance of this SET. So you need to demodulate the signal either using a diode or some kind of a demodulator, and you are going to get the temporal response of this device either in the time domain, or you can also detect the change, impedance change in the frequency domain. So what you have here is you have a aluminum single electron transistor, but there is a electric field, there is a magnetic field applied. So what that means is you don't have any superconductivity. So it's actually a normal metal single electron transistor, and this shows the IV traces for different gate voltages, showing that you have ample amount of charging events going on, or you have Coulomb blockade which you can lift by applying a gate voltage. And the normal resistance of this device is around 195 kilo ohm. And you have the Coulomb blockade oscillation here, and that is the change in the device impedance. This is basically the Coulomb blockade oscillation is nothing but the change in the device impedance as a function of gate voltage, okay, or device conductance. And you can see that the demodulated signal from the RF reflected power is going to exhibit a similar change, a corresponding change, or it's going to mirror the gate voltage. It's going to mirror the Coulomb blockade oscillation as a function of the conductance as a function of the gate voltage. You can capture whatever is happening in the device just by looking at the reflected power. Okay. Now, what you can also do is you can apply a small wiggle on the gate voltage, a small voltage oscillation on the gate that is going to oscillate the impedance of the device with the same frequency, and then the reflected power will be amplitude modulated in that frequency, which you can see as sidebands, which are shown here. Here they have shown only the sidebands here, but the actual reflected power is going to look like something like this. You have this main power, then you have the sideband power, then you have the main carrier signal and reflected power. So this is basically the modulated power, and this is the carrier power. So what we are seeing here is these peaks. Okay. So the signal noise ratio of these peaks can tell you how sensitive this device is, and you can extract a sensitivity, in this case the charge sensitivity of the order of few tens of micro electrons per root hertz for the device. So this device is operating at close to 2 gigahertz, basically around 1.7 gigahertz, and that is the carrier wave you are sending. That is at resonance, and you can detect events close to like a megahertz. Even here it is even 200, close to 200 megahertz in frequency. So where you have, in this case, what you have is you have applied a 200 megahertz signal to the 137 megahertz signal to the gate, and you can get that back by demodulating the reflected power. And that's what this signal is. Okay. So this is the first device, first attempt, and later this technique has been used for detecting real-time tunneling events, capture the electron motion in real time in quantum dots. So in this work, what we have is you have a hybrid device which consists of a quantum dot, gated quantum dot. You can see these bright colored electrodes are gates, and the faint region here, which looks like this, is the superconducting single electron transistor. Okay, and when you bias this at the sensitivity point on the edge of a Coulomb blockade peak, this actually can detect this motion of single electrons charging and discharging events through this quantum dot. Okay, yeah, we can detect these events in real time. Here, others were able to detect in like megahertz time scale, also microsecond time scale, or megahertz in frequency, in the rate, in the tunnel rate. And interestingly, they were able to correlate the tunnel rate that they observed with the direct current measurement. So one axis the current in femtoamp, what they have measured, and what you are seeing here is the current that they have calculated by observing the tunneling events through the tunneling events using the RF SET. In this case, it's superconducting radio frequency single electron transistor. Okay, and they were able to correlate the IV measurements to the current that they have calculated by charge counting experiment. And this is the first experiment where somebody has observed tunneling events of electrons through a solid circuit in real time. Okay, and the sensitivity of these RF SETs have now reached almost in the range of 1 microelectron per root hertz, which is pretty close to the quantum limit, where in this experiment they had an ultra small aluminum SET, this is called island, and there is a source and there's a drain here. Okay, and similar tank circuit as we discussed in the previous slide. The only attractive part here is the detection temperature was like 4 Kelvin, whereas in the previous experiment these are all in millikelvin range. Okay, sub-Kelvin range, close to 10-15 millikelvin. Whereas in this experiment they were able to raise the operational temperature to 4 Kelvin. That is because you have such a small, ultra small tunnel junction, which is of the order of like 50 nanometers or so. But this scale bar is given here. Okay, so that is the story with the radio frequency single electron transistors. Now the same strategy can be applied to the quantum point contact based sensors too, and that is what is done in this work, where you have a similar tank circuit. You have an inductor plus there is a capacitor is connected to the quantum point contact in this charge in this quantum dot. What you have is you have a double quantum dot system here. So you have two quantum dots. When you energize the gates, then you have quantum point contact. Okay, And this quantum point contact is connected to a tank circuit, and you are observing the reflected signal. And this resonance for this tank circuit is around 230 megahertz. It's not in gigahertz. And you can see, as a function of the device impedance, the reflectivity of the tank circuit is changing. This is the reflectivity S11 of the tank circuit taken at various operational points for the QPC, operational regime of the QPC. And as we discussed in the double dot session, the double dot is going to give you a charge stability diagram, which is going to look like a honeycomb. So this region is 0, 0. And you can, as you go, either horizontally or vertically, you are going to fill one of the dots in, okay? And this is the typical charge stability diagram for a few electron double quantum dot. Usually, you get this information by measuring the direct current through the device. But in this experiment, what is done is you have looked at the RF voltage as a function of this gate voltage, dVRF by dVL. And then what it is, you actually have varied VR and VL and recorded this. And you can see that the whole stability diagram was recorded with 1 million data points in a matter of like 3 minutes. That means you have 1 million data points. But if you have a conventional data acquisition protocol, 1 million data points, even if you go the fastest, you assume that you can get one data point in 100 milliseconds. That is really fast when you look at the DC measurement in on these devices. Generally, you need something like 300 millisecond to 500 millisecond is what you need to get one data point. Because remember, you have all these filters and other things in the DC line. So you cannot get anything faster than that, okay? So the 100 millisecond per data point, even if you assume, is going to take 28 hours. Whereas the same is going to take 28 hours, okay? But the same amount of data, same information, you are able to capture in like a fraction of it, in fraction of that time, like many orders smaller, in 180 seconds, like 3 minutes, you are able to get 28 hours versus 3 minutes, okay? So this is a huge technological advancement, especially for these kind of measurements where you need to carry out sensitive measurements, and more the time you spend, you can actually have more noise and all kinds of other issues. So it's important that you finish this measurement much faster to go to your operational interest or point of interest. Okay, so this technology here is showing that you can get the same data in like a much lower duration. Okay, and one issue though here is the operational frequency is like 230 megahertz, and the bandwidth, okay, the bandwidth is like maybe 8 megahertz. That is probably the bandwidth in this case. That means you can detect signals up to like a megahertz, so up to a microsecond, probably something of that order, okay, or like a few hundreds of nanosecond. But of course, that is a huge improvement from your normal DC where you are measuring things in millisecond. But if you really consider the need for error correction schemes and other ultra-fast charge dynamics detection, this is still falling way shorter in detection speed or detection rate. But still, it's a huge improvement from the conventional current measurement through the quantum dot or the conventional quantum point contact charge sensing measurements. Okay.